Hi, my name is Skylar Moe, and today I will be presenting Lab 4 of Physics 2212, which is called Magnetic Braking of Faraday. The purpose of this lab is to explore Faraday's law by observing a magnet falling through a conductive tube of aluminum foil. As we learned in lecture videos, a time-varying magnetic field provides an EMF that can drive a current. In this lab, the source of the external magnetic field was the falling bar magnet, and the induced current was driven around the tube of aluminum foil. I then modeled this interaction computationally. As a summary of my results, I concluded that the aluminum foil tube slowed the rate of the falling magnet, and from my experimental results, it took 1.27 seconds for the bar magnet to fall through the tube, compared to the 1.12 seconds that it took based on my computational model. Some of the physics principles highlighted throughout this lab were Faraday's law, which states that a changing magnetic field can induce a current in surrounding objects, the Biot-Savart law that helps us find the magnetic field of a bar magnet, and Newton's law, specifically the second and third laws that deal with net forces and direction. For the procedure of this experiment, I first had to mark the north pole of the bar magnet, and I did so using my magnetometer app. After that, I held the tube vertically in one hand and positioned the magnet just above the top opening. With my other hand, I held my phone to get the entire length of the tube in frame on the camera. I started recording and dropped the magnet through the tube. Then I found the times when the magnet entered and exited the tube. I did this 5 times to find the average time it took the bar magnet to fall. Now we are going to take a look at my data. I determined the average time it took for the magnet to fall through the tube was 1.27 seconds. Here is some additional data on the length and radius of the tube, the width of the foil, and the magnetic dipole calculation from Lab 2. I also included the mass of the bar magnet that I included in my code, as well as the average time it took to fall through the tube where my calculations were on the previous slide. Now we will take a look at my glow script code. On the left you will see the geometry of the code where I included measurements from the previous slide, including the length, width, and radius of the aluminum tube foil. Step 2 was on the magnetic field function of the bar magnet, so I took that from Lab 2 code, and Step 3 was the magnetic flux function. So here's my code continued. Step 4 dealt with the current in the ring, and Steps 5 and 6 dealt with the magnetic field at each ring. Steps 7 and 8 dealt with the magnet, so that included the net force on the magnet, and the magnet's velocity and position. So here's my computational model results. On the left you can see the tube and the magnet, and on the right you can see the velocity versus time graph. According to my model, it took 1.121 seconds for the magnet to fall through the tube. Now to interpret what my code was saying, the intensity of the coloring on the tube indicated the magnitude of current flowing through each ring. Then the colors red and blue indicated the current flowing in opposite directions. Red indicated clockwise and blue indicated counterclockwise. If we were to flip the magnet around, we would observe the same motion, but the current is flipped since the change in flux direction flips. The computational model is less accurate because it does not account for error or conductivity resistance. The shape of the plot tells me that the magnetic and gravitational forces acting on the bar magnet eventually become zero, so the bar magnet stops accelerating when the forces are equal, and the net force is zero, which is when it is in terminal velocity. Finally, I will answer the what-if questions. The first question is, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? I concluded that the magnet would have fallen more slowly, and it would have completely stopped falling if the resistivity was equal to zero. Using Ohm's law, where V equals IR, if R gets closer to zero, the induced current would in fact be larger. The second question is, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? I concluded that the magnet would fall faster, and if you reduce the number of rings, you would in turn be reducing the induced current.